What's going on? It's your boy, Kenny T, with Kilo Tango Aviation. In this section, we're going over the Airplane Fire Handbook section on what is known as energy management. If you know anything about Bob Hoover, then you've seen energy management at its best. Or if you try to do a power off 180, you know that that's energy management. Or really any maneuver where you're looking at airspeed, altitude, and trying to balance it to make it work. That's called energy management. So when we look at energy management, that's the process of balancing altitude and airspeed, or more technically, balancing potential energy and kinetic energy, control the airplane's flight path and performance. So what is potential energy? Well, your potential energy is your altitude. That's the potential that your aircraft has, or the potential energy that is available to the aircraft. It's a source of energy as potential. The higher the altitude, the more potential energy you have. It's kind of like a ball at the top of the hill. It has the potential to create a lot of energy as it rolls down the hill. That's an aircraft at high altitudes. Kinetic energy is the airspeed. That's the energy stored as kinetic energy. The higher airspeed, the more kinetic energy you have. Together, altitude and airspeed make up the airplane's total mechanical energy. When we look at the airplane as an energy system, the airplane is an open system. So once the airplane is airborne, the airplane gains energy from engine thrust, and so that takes your chemical energy of the engine and turns it into mechanical energy. And when we look at an airplane in the air, you have engine thrust as a way to gain energy, and drag as a way to lose energy. So drag and any other environmental factors. Those are the things that go in and go out when we're looking at that system, which is why it's an open system. Now, when your thrust exceeds your drag, your total mechanical energy increases. So you can store the energy as increased altitude, so you can climb at a constant airspeed, or you can increase airspeed, accelerate at a constant altitude. So one or the other. Now, when your drag exceeds your thrust, so you have lower energy thrust than you have drag, your total mechanical energy decreases. Now, you can compensate this by descending at a constant airspeed or slowing down at a constant altitude. And when the thrust equals the drag, the total mechanical energy remains the same. Now, the airplane can maintain steady altitude and airspeed when we're in this state. In this section, there's a whole lot of different charts that talk about a lot of different things, and I'm going to try to simplify all of those things to make it easier to understand. We're talking about energy management. In this chart here, it kind of goes through all the different scenarios of what happens when you have thrust, which is greater than drag, how you can either increase your altitude or increase your airspeed, and what the resulting conditions are. And those are 6 different conditions that can exist. You can go through these on your own if you like. We break it down. Energy gain from thrust minus the energy lost through drag equals the change in potential energy plus the change in kinetic energy. So your net energy change is also equals to your change in stored energy. Now, how do you, the pilot, the one flying the airplane, how do you control your energy state? Well, there's 2 ways. Your throttle. Your throttle equals your total energy control. So the throttle regulates how much total energy is available to you. More throttle equals more thrust, more total energy available for altitude or airspeed. The less throttle, the less thrust, and less total energy that you have available. And when you take a look at your elevator, that is how you control your energy distribution. So that the elevator determines how energy is distributed between altitude and airspeed. So if you pitch down, you're going to trade airspeed for altitude. You're going to pitch up, you're going to trade airspeed for altitude. You're going to climb, you're going to slow your airspeed down, but you're going to gain altitude with it. If you pitch down, you're going to trade your altitude for airspeed. So you take your altitude, a higher level, and you're going to descend. And by taking altitude, you're going to speed up. So you're trading one for the other. This illustration kind of demonstrates how you can increase your energy gain, thrust, drag, and the net energy flow between your altitude and your airspeed, because it's a balancing game. And here's a caveat to that. So when you're managing energy during flight, understanding that power required curve is critical. On the front side of the power curve, high speed, low angle attack, pulling back on the yoke causes temporary climb, slowing the airplane towards the center of the power curve. This reduces drag and creates excess power, which is awesome. Thrust exceeds drag, which can be used to climb or turn while maintaining a constant airspeed and increasing your load factor. On the back side of the power curve, get low speed, high angle attack. Pushing forward on the yoke causes a descent, accelerating the airplane towards the center of the power curve. This also reduces drag and creates excess power, improving the ability to climb or turn at a constant speed. Having effective elevator control is key to managing energy and avoiding excess deceleration or sink rate, and helps you maintain stable and controlled flight. Now, when we talk about exchanging energy between altitude and airspeed, we've got this chart here that kind of breaks it down. Because we talked about before, we got potential energy and we got kinetic energy. We can trade airspeed for altitude by raising the nose. The airspeed decreases, but your altitude increases. And now we can also trade altitude for airspeed by lowering the nose, which will cause the altitude decrease and airspeed to increase. But the total energy in the system remains the same. You're just shifting between altitude and airspeed. When we look at this little chart here, it's the constant, we'll call it the energy height. So we look at point A, it shows that we're on the 6,500 foot energy height curve. So now when we're sitting at about 6,000 feet, we're 6,000 feet and we're at 100 knots speed. If we're going to keep that same amount of energy, we can trade altitude for airspeed and descend to 4,000 feet, which would then increase our airspeed to 200 and something knots. That shows how we can kind of balance the two when you're in a closed system where you're just trading one for the other. When you look at this chart, this kind of has a bunch of stuff here, but essentially what it's showing is the stuff on the red side is when you have a total energy loss. So if you reduce the power, or how you're going to be in the red area, or if you add power, you'll be in the blue area, which is increasing total energy, which takes you away from this green curve, which is the conservation of the particular energy that you have. So by adjusting the throttle, you're either increasing your energy, which pushes you in the blue area, or decreasing your energy by reducing the throttle, which is the red side of the curve. So here's some energy errors and how to fix them. So if you have total energy error when the airplane has too much energy or too little mechanical energy, altitude and airspeed both deviate in the same directions. You're climbing and accelerating, or decelerating and slowing down. Well, what's your solution? You adjust throttle by either increasing or you decrease. That's what you do when you have a total energy error. Now, when you have a distribution error, this is when the mechanical energy is correct, but you have an energy distribution error. This is when your total mechanical energy is correct, but it's not balanced properly between airspeed and altitude. So let's say your altitude and airspeed deviate in the opposite direction. You're climbing while slowing down, or descending while accelerating. In that case, you have the right amount of energy, but it's just not distributed properly. So you need to adjust your elevator to redistribute it properly and to make the energy do what you want it to do. Now, here's 3 basic rules of energy control. If you need more power, here's 3 basic rules of energy control. If you need more energy, increase the throttle and use the elevator to decide whether you need to climb or accelerate. If you need less energy, reduce the throttle. Remember, we're talking about the entire system and how to increase or decrease the energy within the system. Reduce the throttle, and then use the elevator to descend or slow down depending on what you need. Now, if you want to exchange the energy, you want to keep the throttle constant, but you want to use the elevator to trade altitude for airspeed, or vice versa. Throttle equals energy supply, elevator equals energy distribution. Now, let's take a look at a few different scenarios, and it kind of still goes over the same process or the same concepts that we just talked about. So let's say in scenario 1, you're too low and too slow. What do? Well, you're too low and you're too slow. That means that you got an energy problem and you need to increase the amount of energy in your system. So you're going to increase the throttle and you'll use the elevator to pitch gradually and regain your altitude. Scenario 2, you're too high and too fast. That means you have more energy than you need. So if you have that, how do you get rid of energy? So you're going to reduce your throttle. Then you're going to lower the nose and convert altitude into airspeed slowly. Now, scenario 3, if you need to clear a rising terrain, you need to increase your throttle to the maximum and use the elevator to climb, to hold the nose up to allow for your best climb, which is your VY. But if we want the angle of climb, it's actually VX, not VY. Best angle of climb is VX. Best rate of climb is VY. If you're descending too fast and losing control, increase throttle and pitch up slightly to stabilize the aircraft. So this probably means that you probably don't have enough power in, the airplane is ascending, and also speeding up. So add a little bit of power, which will slow down that descent, level the airplane out, and figure out what you got going on. When you look at this chart, this kind of highlights some of the things we just talked about, what you need to do. So these charts can be a little bit confusing, but there's a lot of charts in there in this whole section. And hopefully the ones that I put in here will make it a little bit easier to better understand, manage your energy. Next thing we'll do is avoid dangerous sink rates. So dangerous sink rate occurs when your altitude and airspeed are both decreasing rapidly. Thrust is insufficient to recover. So you have to recover. You're gonna have to lower the nose to increase your airspeed and then increase the throttle to retain altitude. A lot of times there's errors that happen, and we're going to talk about some of those common ones and how you fix them. So if you over control the elevator, which can lead to poor energy distribution, if you're pulling too much or pushing too much, airplanes not trim, you can end up having really poor energy distribution. Also, if you have bad throttle usage, if you're just throttle jockeying, moving it back and forth fast without actually seeing what the aircraft is doing, you're going to end up with bad energy management when it comes to total loss or too much energy in a particular scenario. The other thing that happens is if you're chasing airspeed to altitude, you're going to be over controlling the aircraft, and that's going to lead to poor energy management. You want to slow down, take your time. Slow is smooth, smooth is fast. So I hope that's a good summary of what's in the Airplane Flight Handbook when it comes to energy management. Go ahead and review it, but like I said, this is a really good overall explanation of the things that are covered in the Airplane Flying Handbook. That's it. Thanks for flying, and thanks for choosing Kilo Tango Aviation.